express discussion, let's go ahead and have that with me later. So it's a great pleasure to welcome Anna Gilbert.
Thank you. So I'm very happy to be here. And so I'm gonna give a talk about a very small part of a larger piece of work. And the larger piece of work has to do with localizing or finding targets or sources of sound in a geographic region. And my co-authors and I came up with a number of algorithms for doing this very efficiently using incoherence of signal sources and sparsity of signal locations as well as signal sources. So it's always a pleasure to come to Maryland and to give a talk that's been supported by Dennis. So thank you, Dennis. So here's the overall localization problem. Your goal is to localize some target that's making noise. So perhaps it's somebody's cell phone ringing in the audience, or perhaps something less innocuous. And so you have a network of sensors. If you're trying to find somebody's cell phone that's ringing in the audience, you have a network of sensors. Sometimes you have other kinds of sensors, but your network of sensors can collect the signal over time, so you can hear it over a period of time, and your sensors can communicate amongst one another what they hear, or maybe they are going to communicate some sort of collection of measurements of what they hear. And then in order to figure out where that target is or where that cell phone is, they solve some sort of optimization problem. Ah, that's my cell phone that's ringing, and I should turn it off. Okay, typical solutions sort of follow the following pattern. You have these sensors that collect signals over time. So perhaps they sample at a very high rate, say even many times over a Nyquist rate. They take this great big collection of samples and they communicate them all across the network. This should look like a rat's nest of cables. This communication of these very large pieces of data might create a huge communication burden. I mean, we heard in Karen's talk about telemedicine and sending all types of information over a cell phone. I guarantee you, if you send lots and lots of information frequently over a cell phone, it won't be ringing very much because you'll run down the battery. Assuming that you do have enough battery, enough power, and enough communication bandwidth to transmit all of this data over the network, typical solutions to the localization problem involve solving centralized, in a centralized fashion, solving an optimization problem. Sort of maximize or minimize the L2 error of where I think my cell phone is in the audience over a very large space. So we want to try and, well, reduce the amount of communication amongst all the sensors. We want to try to reduce the number of measurements that each sensor has to take. We want to try and come up with an accurate and a really efficient solution for solving the localization problem. And so there are a couple of techniques that we're going to use, and the main one is to view solving the localization problem as a sparse approximation problem. And so I'm going to give you a formal statement of the full localization problem, and then I'm just going to talk about one aspect of that localization problem, namely how to find the bearing. So it took me you can tell that I think in Cartesian coordinates. It took me a number of months to get straight. Okay, bearing and range. Okay, this is angle and radius. We're talking polar coordinates. And bearing is simply what direction. And your ears are fantastic at this. You can very easily figure out the direction the sound is coming from. your ears. You aim them all automatically. So when I say bearing, think just direction. Not how far away it is, but just where it is. And your ears do this fantastically well. So I'm going to give a really simple but lovely randomized algorithm that incorporates, well, both the notion of randomization in an algorithm, as well as a key little estimate, which is very simple oscillatory interval. So it's a lovely blend of algorithms and harmonic analysis. And I thought it was a great example of a solution and a problem to give at an FFT. I will give some proofs. It's really very simple, elegant little proofs. And I just emphasize this is a small part of a larger solution. Okay, so let me state this problem like a math problem. We're doing bearing estimation, so we just want to find direction. We don't care so much about how far away something is. And we've got k sources. So let's say we've got 3 cell phones ringing somewhere around us, and they all broadcast some sort of sine wave. And we can arrange at our disposal something like k receivers, so placed somewhere in an annulus inside this larger ring around which our cell phones are placed. And we want to figure out the directions of these 3 cell phones in a very efficient manner. So in other words, we want our sensors to not record very much, and we want them to not transmit very much to some central receiver or some central processor, and then we want the central processor not to compute very much. So we want to do this all very efficiently with a small number of receivers compared to, say, the number of sources. When I say small, I mean k sources and about order of k receivers. So if you think about trying to localize a cell phone and your 2 receivers, that should be sort of your standard. Okay, so here is the structure of the algorithm. So we are going to specify a random placement of the sensors. So remember, we have our sources on a large ring, and inside that ring, on some smaller disk, we're going to place our receivers. And we're going to place them randomly. We're not going to place them in a specific arrangement. We get to put our ears wherever we want them. And we're going to assume that our sensors can generate a list of frequencies that they hear. So there are various ways that they might be able to do this, but let's just assume that it's easy for them to figure out I hear this frequency. And then they're going to send these measurements. So we're going to call this list of frequencies that they hear their set of measurements. We're going to send their measurements to some central processor. The central processor is going to run a decoding algorithm on these measurements. The central processor, we assume, also knows the random placements of the sensor. So it knows where the sensors have been placed, albeit they're placed randomly. And then our randomized algorithm is one that's going to succeed with high probability over the choice of the sensor placement. And the technical description of this is that for each choice of where the targets are, this algorithm succeeds with high probability. It's not going to have super strong failure guarantees, but it'll be good enough for a randomized algorithm. Okay, so like I said, we're going to find the bearing only. So this isn't a cell phone. This is like the phone in my house, and we're trying to find the phone in my house that's ringing. Okay, so to give you a quick back of the envelope calculation, sort of a lower bound of how many sensors do you need to find a target, at least to find the bearings of a target. So if you've got two sensor arrays and phones ringing, these 2 arrays will give you candidate positions at the intersection points of these bearings. Okay, and you actually need a third one to remove a false positive. This gives you some idea of if you know the bearing of a phone, and you know enough bearings, you can triangulate and figure out the exact location. So finding the bearing is actually a pretty good thing to do. Then you can do triangulation to figure out the actual location. Now, I just want to do bearing only. Okay, so here's again description of the setup. The sizes of these rings depend on the wavelength or the frequency, the number of sources, and n here is actually the number of angles that we're going to look at. So it's a discretization of the angles from 0 to 2 pi. And just to remind you, we've got phones on a large ring outside this little annulus, and we place our sensors at random inside this little annulus. Okay, we're going to assume that this ring is far enough away from the rest of these sensors that these sensors see a planar wave. So we're in a far field approximation. So these rings actually flatten out and they see a planar wavefront. Okay. And I'm going to describe the procedure just for one known frequency. If you have a bunch of different frequencies that are heard, you're going to run this procedure for each frequency. So let's just assume, this is actually the hard case. Let's just assume that all the sources use one known frequency. So this sounds like cacophony. You know, you've got 3 phones ringing, all at the same tone, and you've got to figure out where are they. Okay? So this makes the problem harder because they all have the same tone. Like I said, we can repeat this localization procedure at each frequency if you have different sources at different frequencies. This is actually easier. Okay, so we're gonna look at this problem from the source's point of view. Okay, so here's the phone, and here are the planar wavefronts. Here's my sensor, and it sees these planar waves. What the source sees is actually a phase-shifted version of the original signals. Assume that these phones all have phase 0 at time equals 0. And the phase that this sensor sees or observes is a function of the relative bearing of the phone with the sensor. We sort of this is interesting to explain this physical phenomenon to a friend of mine who's a computer scientist. You know, if I have a phone ringing there and a phone ringing there, I hear the 2 sounds with a phase shift between the 2 of them because they're in 2 different locations. And that's how your ears work. They hear this phase shift. Okay, so here is the mathematical description of this phase shift as a function of the distance between them as well as the relative angle between the target and the source. And we're just going to decorate this wave with an amplitude that captures the power as well as, I guess, the phase of whatever the original phase is of the source. And so we're going to assume that our sensor just sees this one complex number. So how it actually goes from listening to a tone to actually determining this value, we can actually talk more about that. But you know, for right now, let's just assume that the sensor can actually retrieve this information. So actually, how you can build a sensor that will listen at a sub-Nyquist rate and can take samples at that sub-Nyquist rate and efficiently determine this frequency is actually part of a much larger, much different talk. But my colleagues at the University of Michigan and at Rice University, we're working to build a sub-Nyquist receiver. So a very highly efficient sensing device that can actually do this. So we actually started as mathematicians with, let's assume that we've built this. How might we use this to figure out where the cell phone is. Okay, so let's just assume that our sensor can hear this and can report this information to a central device. Okay, so if we have one sensor and many sources, what our sensor hears is a superposition of signals which look just like this. So this is a sum of complex exponentials that are weighted by the amplitude and phase of these different sources. And this assumes just plain straight additive interaction amongst the sources. This does not take into account any sort of fading or multipath interactions. We're just going to assume we have this linear superposition. This is how the sources interact. And now, here's how we set up the algorithm. So we have these randomly placed sensors. They can listen and they can hear these frequencies. They can generate these superpositions of these complex exponentials. So each sensor is going to generate a list of the frequencies it hears. We might just assume that it just hears one, just for simplicity. It's going to send that list to some central processor. This central processor knows the sensor locations, the random placements. And this central processor is going to form a dictionary matrix A. And what is that dictionary matrix A? What that is so that it's a short but wide matrix. The columns are indexed by the number of bearings, so the number of possible different angles that your phone might be at. And then the number of rows is the number of sensors. And then an individual entry here is the phase shift that a sensor at position P would hear if it were listening to a source that is coming from bearing L. Okay, so it's some sort of complex exponential of the form, e to the 2 pi omega cosine phi L minus c p. So it's some sort of complex exponential, which is the phase shift the sensor would hear if it were listening to a bearing, if it were listening to a target that comes from bearing L. And then this short set of sensor measurements is the set of measurements that the sensors actually heard. And now what the central processor is going to do is say, I want to actually solve for my source locations. My source locations are going to be a sparse vector. After all, there are only 3 cell phones. And this set of measurements has got to be consistent with this product. In other words, this set of sensor measurements has got to be what each one of these sensors heard, given a source at this position, and this position. Okay, so here we have an under-constrained linear system with a short, fat matrix, where the unknown vector, well, it's unknown, but we do know that it's sparse. We know that it's really sparse, and there are only a very small number of non-zero entries in here. And what problem, this is basically a sparse approximation problem. Here is our known signal. Here is our redundant dictionary, many more columns than rows. And our set of sparse coefficients is simply our unknown, our source locations. And so what we want to do is we want to solve for this sparse set of coefficients that is consistent with the sensor measurements. We want to solve a sparse approximation problem. And our redundant dictionary is this one that's derived physically. It consists of what the phase shift would look like at sensor P if there were a target at location L. Okay, so let's get a little more mathematical. Exactly what is this? What does this dictionary look like? Okay, this dictionary looks just like this. Nothing more. This is a far field approximation for the phase shift. If you're standing here and there's a cell phone ringing over there with frequency omega. Okay, and these coefficients are simply the source locations. So there's been a large body of work over the last couple of years on solving sparse approximation problems of this form. The literature calls this a compressed sensing problem. Although I would hesitate to call this particular problem compressed sensing because this is a dictionary that is derived from both the physics of the problem as well as the algorithmic machinery of place these sensors at random. Okay, so maybe what I should also point out here is that these angles, these correspond to the sensor angles. These are random. Okay, and then these are arbitrary. These are where the target locations are, or the bearings of the targets. And so this matrix ALP is some sort of random complex exponential dictionary, but it's one that's derived from physics rather than drawn mathematically, abstractly out of the air. Okay, so what are we going to do? We're going to solve for the locations of these non-zero entries with a really simple brain-dead algorithm. And we're going to figure out what locations are consistent with the measurements that all these sensors collected. Okay, are there any questions? This is like the main hard part of this problem is setting it up. The algorithm is trivial. Yeah.
You assume that all the sources have exactly the same phase, right?
Yeah.
This is pretty unrealistic assumption. I mean, in real life, they will all have different phase shifts, and will your algorithm work in this case?
Yeah. So the algorithm is actually more robust than you would think. We've actually tested it out in a bunch of different ways. But yeah. And you know, this linearity, you know, no multipath, whatever, that's also bogus. But just the setup like this, okay, good. Okay. Now this is the algorithm. This is it. So what do we do? So we want to know, or we send as input to the algorithm the number of sources. How many cell phones are we looking for? What is the dictionary? So this is what the central processor derives or builds, knowing the locations of the sensors, and then the set of measurements y from all the sensors. So they all have to communicate to one another, to the central processor, and then we just output a list of the locations of the targets. So we just run a greedy pursuit algorithm, so we iterate some number of iterations. The basic idea is that you take the adjoint of this dictionary matrix A, you take A star, you hit it against the set of measurements y. This produces some great big long vector of length n. N being the number of bearings that we're looking for. Threshold that thing, keep the top k, or top order k. Toss that into add that into your current residual. Threshold that thing, because you actually want to keep a list of just k, or roughly k, locations. You don't want to have k and 2k and 3k each time you march through here. So threshold that thing, and then remeasure. So in other words, take A, your dictionary matrix A, apply to R, remeasure this current residual, subtract from the given set of measurements. This gives you sort of the error. And then iterate. So you're pulling off where you think the target locations are sort of greedily, roughly k of them at a time. And this algorithm is really kind of brain dead as given here. You can make this much more sophisticated by saying, suppose I actually have some idea of the strength of these targets. I can actually estimate the energy of the signal that I'm receiving each sensor. So I can actually start to decorate. I can decorate this residual with the coefficients. I can make them not just ones or zeros. In other words, is there a target there or not? But I can actually start putting in coefficients. So what I think of the strength of the signal, or possibly some sort of probability that there is a target there or not. And then I can start to do more sophisticated things in here by estimating my coefficients. residual. So this actually becomes more robust than you would think.
Output filters knowing number of sources,
It's actually not. What's sort of more of an issue, at least the preliminary results tend to be, is how much do you threshold? And you know, how much do you threshold, and also what is the relative size of the inner radius compared to the outer radius as a function of the wavelength? And so far things don't seem to depend too much on the wavelength, but this ratio of inner to outer radius is going to make a difference. You'll see in a second that theoretically it makes a difference knowing K in terms of being able to argue that this is a good thing to do. This is a good step. Okay, so what is the key estimate? So the key estimate in this procedure comes from looking at this matrix product A star A. So I'm going to take my short, wide matrix, which consists of these complex exponentials. I'm going to take its adjoint, and I'm going to multiply them. Okay, so I want to know what is the effect of taking column M multiplied by, well, column M, the adjoint, column M over here. Are they correlated with one another, or are they not correlated with one another? So these columns, remember, index bearing. So if I have two targets, one at angle L and one at angle M, are the phase shifts that you're going to get from those two signals, are they going to cancel one another if I multiply and integrate? Are they gonna reinforce one another? Like, they cancel enough is the answer. Okay, and so what that means is that if I take as my unknown vector, just imagine a thought experiment, my great big long unknown vector, it's got non-zero entries here in just a few places. When I form A star A and then multiply by this vector that just has a few non-zero entries, what I'll get out is just a few more non-zero entries than what I started with over here. In other words, pairwise distinct columns in this matrix they're not quite orthogonal, but they're orthogonal enough for us to be able to pick out at least the indices of the non-zero or the large entries in a vector like that. Okay, so let's make this idea more rigorous. So let's just talk about estimators. So we actually want to estimate this coefficient x of n. In our simple setup, it's either 0 or 1, but it might actually be the amplitude or the power of a tone that we hear from a target at position m, and we're going to estimate it by taking the nth column of our technical term is called a steering matrix. We'll take the nth column of our steering matrix and then multiplying it by the set of measurements that we obtain. Our set of measurements is actually this linear combination of the targets that we hear and the columns that we hear. Okay, and so what we want to show is that the expectation of this estimator is the right value. In other words, it is x of m. So remember, these guys are random. So this is actually a random variable. So we want to show that on average, this estimator returns us the right value. And just showing that the estimator is unbiased, that you get the answer correct on average, is not really good enough. You actually want to show that the variance is fairly small. In other words, if you take two different columns, AM and AL, that you don't confuse them for one another. So in other words, you can distinguish a target at L and a target at M. So we're going to show that this variance, not that it's really small, but that it's at least smaller than 1 over k, the number of targets. And how do we do that? Well, so this is our sort of physics experiment. Imagine you've got a phone here, and the wavefronts that it generates, that this sensor sees, look like this. And then if I have a sensor somewhere else, a target somewhere else, it's going to generate planar wavefronts that look like this. And by the time this combination gets over here, they should cancel. Or they should be small enough. Okay, so in a second we're going to go through showing that this is the right value. Okay. Let's hold off on proving this for a second, that this expectation is small enough. Assume that this is small enough. Show that the variance of this estimator is low enough, also like this. And then once you have an estimator that is correct on average, so it gives you the right number, reasonably okay on average, and has low variance, then if you repeat, if you take, let's say, k independent copies of this estimator, then you can decrease the variance even more, and with high probability you get a good estimate of where you think this target is. Okay, so how do we bound this guy? How do we show that these phases cancel one another enough? Well, the trick is actually noticing that this expectation is an oscillatory interval. Okay, so it's an expectation over where we place the sensors. Okay, so we get to place them randomly. So we actually, randomly meaning we're going to place them anywhere we're going to place them in an annulus at any angle. Okay, so we're going to integrate from 0 to 2 pi. So that's our distribution. And what are we integrating with the integrand? Well, it's this expectation. What are these two guys? This is a complex exponential with angle m and one and angle L. And if you actually work out the algebra, it's an integrand which looks like this. This is an oscillatory interval. E to 2 pi I k squared cosine minus phi. We integrate phi from 0 to 2 pi. So we actually plot this. It looks something like this. So it doesn't cancel exactly, but it cancels enough. And you can bound this by something which is order 1 over square root of k squared. This in here, so this is order 1 over k. This is good enough to show that the expectation is unbiased enough for us to get a good estimator out of this procedure. In other words, you can distinguish a target at position L from one at position M as long as it's at least 1 over k in size, which is correct if you have about k. Okay, then this is just a standard argument to say that if I have an estimator whose expectation is about right and whose variance is low, then if I take log 1 over delta copies of this low variance estimator, then with high probability, and then if I take a median over these log 1 over delta copies, then with probability 1 minus delta on k log 1 over delta sensor measurements, I will get a good enough estimate for me to be able to find my targets. So this is sort of the technical probabilistic machinery that gets used repeatedly in randomized algorithms to prove that with high probability, these two steps give you the right locations of the targets. So first of all, you form A star Y. So these are all these different dot products, AM times AL. And then thresholding says just take the top 5K of them. The correctness of this procedure is in the proof of the results that I just gave. These two steps are correct and will succeed with high probability. Okay, so the main observation of the main calculation is that wavefronts that look like this almost cancel one another. And that's nothing other than physics or oscillatory movements. All right, so we set up some of these experiments. We've done, well, we've done some simple ones, and what we really are working for is a complete end-to-end system. So the first thing you might want to ask is, so how many sensors do you need to find the bearings of about k different targets? You know, we have 2 ears. We do really well with our 2 ears. So this algorithm looks like you need about 4 or 5 times more sensors than you have sources to get, let's say, to succeed with 95% probability. It's not quite your lower bound of k or k over 2 for bearing. It is independent of wavelength. Like I said, our main motivation is to build a complete, incredibly highly efficient end-to-end system of sensors that can sample at a sub-Nyquist rate, generate these lists of frequencies very efficiently, send really short lists of frequencies to some central processor, and then have that central processor efficiently figure out the bearings of these targets. And then once you have enough bearings, you can triangulate and then get the actual location of these things. So let me summarize by saying this is a really simple algorithm for detecting k sources using about k log for delta sensors. There are a bunch of other types of matched filter and threshold algorithms for localization, and this actually proves that this approach is correct with this kind of simple randomized setup. And I should emphasize that this is just a small part of a bigger framework for exploiting sparsity. Are there any more questions? Yeah.
Yeah, if you look at the question of resolution with respect to speed, with respect to bearing, how close together can two sources be?
Yeah. So what is the Rayleigh resolution of this? So we are running experiments.
Tell them apart.
Yeah, we are running experiments this week to figure out how close you can make these as a function of wavelength and the ratio of the inner to outer radii of the placement of these things. I have, so one of my colleagues, Volkan Chetar, on this is an array signal processing expert, and he's the one that I asked about, does this sound right? And he's still trying to understand, how does k and lambda and R1 and R2, how are these all related to one another?
Okay, so your output matrix and what can be like the output of a beamformer?
It's like a standard steering
So
matrix.
each sensor contains an array, is that what you're telling me?
No.
Or are the sensors, do the sensors themselves form an array?
Well, okay, so the way I had been thinking of it, you have a central processor forms this matrix. And it's different from a standard steering matrix in that the positions of the sensors are random. So it's actually a randomized matrix, whereas usually they're fairly...
Yeah, but they're known though. They're random but known.
Yeah, random but known. Yeah, I mean, it's like in a sonar application, you have a towed array, and you know where your sensors are if you're dragging behind the boat. But maybe some of them died at random. Maybe some of them stopped taking measurements of them. But you know where they are.
So what is your antenna here? What is your array? The sensors.
So are you talking about what is the matrix, or what are these actual?
What is the array? What is the array? It's made up of all these little sensors?
Yeah, so I just think of these little sensor devices as receivers that can listen.
Form an array.
Yeah. They're just placed randomly. Yeah.
You said that we can decrease the probability of failure by repeating the measurements. Did you mean that in between measurements we shift the sensors to a new random position?
No. All I meant was just take more.
So they're the same position all the time?
Yeah.
Okay.
You could move them around, but that assumes that you can go into wherever you are and to mess with them.
estimating the integral, estimating the integral, I think you mentioned that you also changing position of sensors.
So okay, so
This is totally different.
okay, so I think of the measurements as being like this, and you can divide them into blocks. You can divide them into, say, k blocks, each of size log 1 over delta. So when I say take repeated copies, I mean make sure you have a total of k times log 1 over delta, and then in each one of these blocks take a mean. So you have, actually this should be the other way around. These are k, and this is log 1 over delta. You average over k, over blocks of size k. That gives you log 1 over delta different values. And then take a median over those. So I don't mean throw in more sensors. I just mean arrange your computation over the collected set of measurements different. That's all I mean. Yeah.
In your intended application, can you choose the locations of the sensors, or are you constrained to use sensors that are being chosen for you?
So we're mathematicians. So, well, at least Martin Strauss and I are. So we just assume that you could place them at random.
So you can't answer that question. If there were some advantage to be gained by being able to choose your sensors, would you be able to locations? Would you be able to do that?
That's actually hard, because what you're trying to say is I want to create a deterministic steering matrix that has all the properties, all the good properties that I get out of a random one. So actually what I had in mind was you had a known configuration of kind of lousy ones that would break every now and then. And so that you would actually get a...
So in that sense, that you're wanting to allow for the fact that they could break, then you really don't have control over their locations.
Yeah.
Although you could design your array to have certain locations.
So designing your array...
I know that I understand that problem.
It's
That's
really
my
hard.
question. Can you if you have an option and you knew how to design arrays in that respect, then there would be an advantage to.
Yeah. I mean, I actually think the randomized analysis tells you you should try and come up with a deterministic configuration with the same sort of, almost orthogonality of columns property. So I actually think that the randomized analysis gives you a guide for a good way to construct a deterministic one, but that's actually non-trivial.
That you had a list of frequencies that you separated, so you assume that you have just a finite number of pure tones, or?
Yeah. Yeah, I mean it's not totally unreasonable for phones. I also had in mind, when you hear a piece of music live, you can figure out which instrument is where on the stage. So they're playing tones, and you can figure out directions. Yeah, it's not totally crazy. Yeah.
Actually, I guess I'll have to a question and a remark. In case you're talking about the microphones, for instance, if sensors are relatively close to one another, the noise field might actually be correlated. And in that case, in terms of the statistical properties, because of the coherence, that might affect a bit the results. But the question that I have is, in fact, about the Bayesian. You mentioned the Bayesian framework. So, could you maybe say a little bit more what exactly you mean by that? I mean, the expectations you compute are respect to the sensor positions, or variance and so on.
So perhaps to also answer your question, this is a really simple example of something bigger, which is part of some Bayesian framework, where you try and fit a model for the number of sources and where they are, and you either exploit spatial sparsity, in other words, you don't have very many sources, and they're spread out, or sparsity in the types of signals that they're transmitting. So, like they're either transmitting pure tones or a signal that's sparse in some other basis. And so, in trying to solve a maximum likelihood problem, you impose a sparse prior, and so you can actually solve that sort of optimization problem more efficiently with this sparsity. And I just wanted to talk about this simpler piece.
Very well chosen for the time that we have, but I encourage further discussion at the lunch break. That was great, Tony. Thank you very much.